Good evening. Pleasure to be here this evening and talk about something that I'm really excited about. So definitely looking forward, but it's something that I think is potential to change a lot of the things that are going to happen in the way we build semiconductor circuits in the future. Now, let me first give you some background. The reason I got to this was kind of through an indirect route. Over the last 7 years or so, I've been working with my students on brain-machine interfaces. The idea of interacting, basically have interface circuits that talk directly to neurons, measure neural activity, but also can stimulate neural activity. And you connect this into a feedback network, and you can do all kinds of interesting things. Primarily medical right now, basically people addressing a variety of neurological diseases, people that have paraplegia, spinal cord injury, ALS, but you can think about a much wider range of them, Parkinson, depression, a bunch of neuropsychiatric diseases, and so on and so forth. So primarily focusing on the electronic side of this, right? Basically trying to build really images of direct interactions with brain tissue. Now while doing so, I got into interaction with a lot of neuroscientists and started interacting and learning what they were doing and what was happening, for instance, in the world of computational neuroscience. And what happens indeed is that due to the fact that we're building much better imaging strategies today, we're building all kinds of ways of measuring and seeing what's going on in the brain, we also start understanding more how the brain is working. And then the thought came up, would that really help us? Wouldn't that not be of interest if you start understanding that? Could we apply some of that in the reverse direction and see how some of the knowledge of the brain can help us think about different or better computing systems? And that's the way I got to this particular topic here. So, here's a question that we should ask ourselves, right? A lot of research that we're trying to do is based on kind of, you look forward into the future, you see what's happening, you have roadmaps, and then you ask yourself questions. You say, if this would happen, what would we do? What are the opportunities that arise? What are the challenges that arise? And that allows you to create some vision. And then you work backwards. You work backwards and you find out what challenges have to be overcome to get to that vision. So here's one of those questions that we've been asking ourselves quite a bit. How to perform high fidelity, efficient computing on platforms that have huge numbers of lousy components. Like transistors which are not as good anymore as they used to be. These are also known as nanodevices. If you look at nanodevices, you know there's a lot, the time of this very nice switch we had in the digital world for a long period of time is kind of vanishing. So that's the question you ask yourself. And you say, well, what might be an option? Here's one particular way of looking at it. So far, a lot of what has happened in the world of information technology, computing, and so on and so forth has been driven from the 50s on this very simple abstraction of deterministic computing. The idea that you can build a machine, and every time you execute that machine with the same inputs, you get the same outputs. Fully deterministic one-to-one mapping. There's a whole algebra behind that. Now that's a great abstraction. It has helped us amazingly in building computing engines that are really baffling. But at the same time, it's getting harder and harder to maintain that. And I'll explain why that is. It is too expensive. And it really is limiting how we can go forward into scaling energy per operation, size of operations, and so on and so forth. So the alternative would be, say, to abandon determinism and think about statistical computing. Computing, that's approximately accurate. That gives you distributions, not direct final answer. And if you look actually what a computer that exists that exactly does this, is actually the brain. The brain is indeed a statistical computer. It's not a deterministic machine. And it has some other properties. It basically uses statistical inference as a basic mechanism. It has massive redundancy. I'll come back to that a lot. It uses many, many neurons. We have tens of billions, 100 billion neurons just right here. And they work on low resolution computation. They don't really have 16-bit or 64-bit floating point type of data representations present. So these are kind of the big picture of what I would like to present today, and I'll give you some examples of how we can get there and what are the opportunities. Now the question is again, why now? Why are we asking this question ourselves right now? And indeed, I'm not the only one. You just look at popular press, you see a lot of these neuro-inspired things everywhere popping up. A couple of reasons. It's always good to look backwards. Obviously, neuro-inspired computing is not new. It has been around for a while. People have been thinking about maybe we can build machines that basically learn and compute just as the brain does. Actually, it goes way back to the 40s and 60s, 1900s, I mean by that. And the work of McCullough and Pitts and heavy learning type of concepts were basically invented at one time. A lot of excitement. And then Marvin Minsky at MIT in 1969 wrote a paper that said this is all kind of doesn't work at all. This is basically, I can write any single algorithm that does better at this type of things. So it kind of comes up. And it was very quiet for a long period of time. Till approximately the 1980s came along, and then the concept of artificial neural networks basically arose again. Primarily because of Hopfield networks were a concept that basically was introduced at that point in time and changed the picture again. And then you had Carver Mead, basically after he had done his VLSI revolution book in the early 80s, towards the late 1980s, he really became a very strong believer in analog neuromorphic computing. And he wrote a book about it, got a lot of people excited, got a whole bunch of things going, and then it basically went nowhere again. And it went quiet again. Till, after I would say the last 5-7 years or so, suddenly it's back. And there's a couple of reasons that you may think why it's back, and 3 of them I'm basically going to enumerate right here. The first one is that in that period of time, as I said, we start understanding more how the brain operates. Not only at the basic neuron level, but basically of the networks of neurons, different functionality levels, and so on and so forth. The other thing that's happened is suddenly these artificial neural networks that basically were kind of shot at basically very infantile and not doing very much, became very powerful. Deep learning now is being used by a broad range of companies to solve classification problems and other ones as well. Self-learning, it's amazing what's going on in that space. And the third one is the fact that computing is not the same anymore. We are indeed looking at other ways of doing computing in light of some of the things I will show you in a second. So this is where we're at right now. Now, obviously, you can look at this in many different ways. Actually, you can basically interpret this as I can go back and build large artificial neural networks, or maybe I can basically use some of that learning we have from the neuroscience computation, neuroscience, and try to think about models of computation and things like that at a higher level. So, let me first give a couple of reasons why I think we have to basically start thinking about different computational models. You've probably seen this slide before. I think every presentation I've been on over the last month, everybody has the same picture in there. They show what happened is indeed that if you look at CPU trends over the years, and you see that we still are putting more transistors on our CPUs, but power has basically flattened out, performance has flattened out in terms of clock speed, and even performance in basically functionality per processor basically hasn't gone up that much anymore. So speed, energy, and efficiency, as well as economics, are plateauing. That's one thing that's happening. Okay? Now, the question is, what are the key reasons that some of the things are happening? And it's all about the fact that obviously our nanodevices or CMOS transistors, when we scale them down, basically have some fundamental properties and some fundamental problems. This is a big one. The fact is that we basically cannot scale energy very much any longer. Energy per operation. Right? Energy is CVDD squared. That's for any operation. Capacitance still scales a little bit when we make the devices smaller, but parasitic capacitance becomes the dominant factor. So we don't gain linearly the scaling anymore. And VDD is stuck. We cannot scale VDD very much anymore for one good reason, it's leakage. Leakage basically is the limiting factor. The fact that we basically have some threshold device, we cannot scale a threshold any longer anymore, and as a result of that, we're stuck at how we basically are low in our supply voltage. And it basically means that your energy per operation doesn't move very much anymore. Now, to my knowledge, if you want to build a more dense computer that does more, you have to scale energy per operation. Otherwise, you just create a machine that's going to explode internally heat. Right? So basically, energy scaling per operation is an essential thing we have to be able to try to figure out how we can get it. And the other one, basically, that's limiting what we can do in terms of scaling is variability. Variability of our devices, variability of our networks, of the wires, and so on and so forth. It's variability basically means uncertainty. Right? It's something that says, well, I know approximately what the value is going to be, but my current might be this much or this much, my threshold might be this much or that much. You don't know. So how do we deal with variability? It's margining. It's the only way to it. You turn something which is statistical, because anything with variability is a statistical thing. You turn it into something deterministic by basically being 3, 6 sigma out and make it deterministic. You know, in all cases, or 99.9999% of the cases, we don't be safe. No, that's expensive. And again, it's going to limit what you can do in terms of energy scaling. So energy scaling basically stops if you basically follow this. Now, on the other hand, there's a set of devices out there that are quite attractive. A set of technology developments that are quite attractive. That basically might help us to move forward, to put more devices together, to put them denser, and so on and so forth. On one side, there's a lot of carbon work going on, both in the 2D space and the 3D space, carbon nanotubes, carbon nanowires, but you have also graphene and all kinds of new 2D materials. There's spin devices, DNA computing, organic, a whole bunch of new devices out there. That might be interesting. That allow us to keep on scaling dimensions up and put many more devices into a fixed volume. Actually, one of the things that basically a lot of the technology support as well is something which is very hard to accomplish today, is through 3D integration. Stacking devices on top of each other and have a 3D device. So that's an opportunity that basically, I think if you think about 3D, it's going to give you a huge increase in 3D, or basically in density. And then we have another thing that's kind of very interesting what's happening is this new set of memory technologies that's emerging. Phase change memories, you have spin memories, or spin torque, you have the RMs, all kinds of resistive memory cells, and so on and so forth. So there's a lot of opportunity out there. Beyond CMOS, there's a lot of life, but all those devices have some issues. And they're not very reliable. The chance that you're going to make a big device which has a trillion switching elements or elements on there, and they're all going to work is about 0. Right? So reliability is an issue. They're going to be variable. They're going to be all over the map. So variability is something that's going to be with us. And they're slow typically. They're not as good as actual performance energy-wise. There's some big questions as well. So there's an opportunity there, but there's some challenges. So that's from a device perspective. But now look at the other side, from an application perspective. A lot of opportunities as well. You might not have noticed, but the world of information technology has changed substantially. We used to be a world of computing. Computing was the key thing. Okay? Nowadays, people don't talk about computing as the limiting factor much anymore. It's about the amount of data you can manage. We shifted from computing as a driving thing of how much data can I move around, how much data can I basically process. So this whole thing of big data is changing the mindset about what computing means. It's basically information extraction. Information extraction from all those type of things that we create. If you look at all your data farms that we have out there, all those giant collection machines, social networking, massive amount of data, and we wanted to extract information from that. That's kind of the key driver below a lot of the information technology architecture we're seeing right now. Machine learning plays a big role in this. Actually, machine learning has become a big aspect of this. Unfortunately, those things require servers, thousands of servers that take megawatts of data today. So maybe we should rethink how we can build computers in light of the fact that the key challenge is how much data can I process. And again, there's where some opportunities lie, right? If we basically see what's happening is that we see a shift away from processing being the core of the operation. Now we start putting processing more and more into the memory, and we come to something which is called memory-centric computation, where the computation starts to be done into the data. So that's an important trend as well. And again, I'll basically later on show you how this gets actually, how this very nicely matches to what's going on in our head right now. And here's another aspect of it, again, the same story really, but it's from the other side. You have the data centers. On the other side, we have what's going on with IoT, sensor networks, swarms, all those kind of things. The idea we don't have trillions of sensors spread around the world. All those sensors creating information, data, and trying to do something useful with it. Now, you can imagine, if I basically send all that information from all those sensors right away to your data servers, the data centers out there, you're going to swarm the network. It's not very intelligent, it's energy hungry, and it basically pushes against capacity. So one of the things to get around that is say, well, rather than sending raw data, why not do processing up front, extract some information at the source. This is what I call in-sensor computation. So you have the in-memory computation, this is the in-sensor computation. The sensor are very small things, trying to extract some meaningful knowledge from the sensors and only send the knowledge forward to the other parts of the system. That requires very low, basically high computation complexity with very low energy computation, because some of those sensors basically are sitting below minimum levels. So these are all kinds of things that basically are set in the landscape. Right? So, as I said, it's probably worthwhile as a result of this to start rethinking about the way we may be doing computing. So I already mentioned one way to do that is step away from determinism and go to what we call statistical computing. Let me explain it this way. Here's your typical integrated circuit stack, or your information technology device stack. Somewhere you have transistors. Now, on twist and top of transistors, we put circuits, and then logic, and we make modules, and we make processors, and so on and so forth, and ultimately you run algorithms on them. That's the stack that you basically have. You're very algorithmic centric. Right? What you do, most of the computation you do is basically algorithms we execute. Now, the problem here is the polygon. As I already mentioned, the devices are statistical. They're not, any transistor is going to be different from any other transistor. And the distribution of the variance is actually increasing. Algorithms have to be deterministic. At this point in time, if you basically have an algorithm that basically gives different answers depending on if you have the same inputs, people will be very upset. Yeah? So this doesn't work. So the way you do that is by putting layers in between that make sure you have that deterministic impression, even though the devices themselves are statistical. By putting margining in there, error correction, all those kind of things will build up to make something look really correct all the time, or basically deterministic. Now here's another thought. Suppose I can do something which is more statistical computing, where computation gives you not a single answer, but a distribution. If you do that, so suddenly that big gap that I have between statistical, because what circuits and logic have to do, this inefficiency layer of this introduced might go away. We might start to think about computation that's done at a much lower SNR value. That basically occasionally makes errors, it doesn't matter. As long as I can control the distribution in the end. That's the key factor. Now you may say, that's a great concept, but hey, there's so much computing going on already, and it's all based on those algorithms. Are you now basically inventing something that does have no usage whatsoever? Now, let's start thinking about the applications that are basically becoming more and more interesting. I said all those sensors out there that we have, trillions of sensors. This is all basically information what they gather is not deterministic, they gather distributions. Okay? So the information we're dealing with itself is not a deterministic thing, but basically it's a set of distributed statistical numbers or statistical process we have. Actually, most of the applications in that realm basically have to do with how the physical world is going to interact with the cyber world, or me as a human is going to interact with information. User interface, in other words. So how do I, as a human, extract information, get knowledge about myself, and so on and so forth. Now, if you look at all those applications where you have human cyber interfaces, all of those tend to be purely statistical. Anything which is basically done in sensory interpretation, feature extraction, classification, recognition, synthesis, all those things are statistical processes, as far as I know. Think about classification. You go to Google, right, and you type in a keyword, and you get a list of things. There's no determinism in there. Actually, this is based on some weight factors, and they basically create a distribution. And what they hope is that the top layer is matching what you're looking for the best. Now, if it shows up at number 2, who cares? At least it's on top of the list you're having. So it's a purely statistical process. So a lot of the things we're doing in computation today are basically statistical algorithmic type things, but we execute them on deterministic computers. Maybe we can use that opportunity to do something different. So let me give you an idea about what statistical computing is all about. Right? If I take a traditional Boolean type of system, or a Neumann computer, you put a bunch of inputs, and you take your inputs, and you're going to map, the inputs are going to get mapped into a single point in the output space. Okay? That's really what you get. That's what determinism means. In a statistical world, basically, the output space is not a single point, but is a circle, a distribution. And again, I'm trying to control the mean and the variance of that output. Obviously, if it's all over the map, it's useless. Now, analog designers understand this very well, because analog design has been always like that. Right? Analog circuits never basically give you a gain of 102.5. Right? You get somewhere a mean and you get a variance on it, and you try to control the basic distribution. So analog designers have always done statistical design. But digital computers or digital designers have not done that. So this is the idea that you still use digital encoding, and that errors may happen. Errors or things like that, you say, okay, if the errors happen, who cares? As long as I make sure that the ultimate distribution is controlled. And you basically have a bunch of mechanisms to do so using estimation, basically control around it, and so on and so forth. There's some examples of statistical computers out there right now. This bunch of work that has been done as part of the FCRP StarNet program, sponsored by the SRC and semiconductor companies as well as DARPA, building statistical computing engines. And they have some interesting results. One example I show here from UIUC, which was called algorithmic noise tolerance. It's like for basically image processing, video processing. So rather than basically say I'm going to use my DCT block or my motion estimation block, and I'm going to make it always correct, I'm going to run it at low voltage. It's going to make errors occasionally and have a way to basically capture errors and correct it on an algorithmic level, not using pure error correction algorithms. So that's the work by Nara Shamba, basically showing some ideas. Again, that's pure statistical computing. Now I'm going to go one step further and say there's one machine out there which is also statistical computing and actually does energy computation very efficiently. So that's the next step. So I'm going to go to Neuro-Inspired Statistical Computing. That's my next step. So statistical computing is one assumption. The second one is kind of basically use some inspiration of what the brain does to make my computation more effective, or be able to scale computation into the long-term future. Now, what do I know about neurocomputing? Anytime you talk to a computational neuroscientist, the first thing they're going to say, we don't know anything yet. Job security, I guess. Now, it's true that indeed we understand some parts of the brain, we understand some things. There's a lot of things we don't understand yet. We learn continuously. But there's a couple things we know. Number one is that if you make an estimation of the computational complexity of the brain, what it does in terms of computation, how much it can do, you start seeing that you make a good estimate is about 16 flops, 10 to the 16 flops per second in terms of computational complexity. That's an estimation, by the way. I might be wrong by a factor of 10 in both directions. But still, it's a good number, because the other thing we know is that the brain, on average, uses about 20 watts. It's like it's like on LED light bulbs. 20 watts, which is 20% of your body power. Your body typically, on the average, uses about 100 watts. Now compare that to some of the processes that are out there. Right? So if you now translate this into, I say, okay, I'm looking at the equivalent inversions and what does it take to do an inversion in, say, the 22 nanometer technology, and you compare the two, you see that the brain is about 2 orders to 3 orders of magnitude more energy efficient than silicon today, in terms of energy per operation. So it shows there's actually some opportunity here. We might learn something to make computation more energy efficient. The other thing that we know is that it's very robust. Well, it's kind of robust, right? Most of the time we operate correctly. Okay, so there's a crash, but most of the time we operate correctly. Now, the components themselves are not very reliable. We lose neurons all the time. And the older you get, the more you lose. Right? I agree. At some point in time, you start to realize that. There's also huge variability. If you look at over the typical neural response, and you compare the sigma, the variance, over the mean, you get a factor of 1 approximately. So huge variance over the individual neurons. Every neuron is different than the next one. They're not basically identical components. The other thing is that devices themselves are very mediocre. They're slow. They're very slow. And still, they can get to some amazing performance. Like for instance, if I look at the auditory system, listening, right? The neurons themselves, the cells, have time consists of about 1 millisecond. Right? They basically fire about at the rate of about 1 kilohertz approximately. Right? Now, at the same time, using lots of them, I can actually listen and basically discriminate between signals from different parts with time constants of about a 10 microsecond, which is 100 times better than the individual component. So you can get amazing performance with mediocre components. And same thing is true with the olfactory system. If you look at your nose, you have a lot of lousy sensors in there, but together they're doing an amazing job of taking basically the different odors apart. And you can look at any part of the sensory tract, we see the same thing. So these are kind of interesting features that we have. Now we look at some of those features, we see mediocre, not very component failure. It makes me think about nanotechnology. Lots of devices, but kind of slow, very unreliable, high variability. Okay, so some similarity may be that we could use to build or think about network computation. So what's the opportunity, I think, of Neuro-Inspired computing? There's a couple of ways of looking at it. I'm going to basically present one corner. Say, okay, what we can learn is that by talking and understanding what the brain does, we may come up with some approaches, some architecture, some functions that we can basically use to build better computing elements. And to me, the key things are number one, massively parallel computing. We're not talking hundreds of thousands, we basically have millions to billions of devices running in parallel. So massively parallel, very high density. So this 3D integration is very important. We get a lot of devices in a very small volume. Major redundancy. I'll show you in a second what's happening. The redundancy in the brain is actually huge, and that's what makes it really work. It's however is efficient. You think about have all those billions and trillions of billions of neurons firing, that thing must be hot, right? Well, it turns out the brain is very sparse in its computation. At any point in time, it only fires up certain regions. It is very, very, very careful and very careful in the way it fires operations. So it's very sparse, computational density-wise, and it operates at low resolution. SNRs of the signals we're basically working with are very low. No big signals. Things are sitting there about 100 millivolts approximately. That's a good signal that you might have. So much lower than what we basically use in circuits today. It is, however, robust, as I said. And the reason it is robust is because of the fact that it uses this redundancy, but it also exploits variability. It exploits randomness. So rather than making the enemy, it basically uses it. And I'll show you some examples of that in a minute. And the other thing basically, so if you look at variability, there's two parts. Some of it are random. I can use that. Some of them are systematic. Now anything is systematic I can learn. If I basically learn a distribution, I can learn that, adapt to it, we're fine, right? Again, that's something we already have learned how to do in analog design. Today, analog design, you measure the circuit, and you adapt your parameters, and you basically tune the circuit. Okay? It's the same thing happening here. Now, you combine this with the features of nanometer CMOS, that says huge number of devices, possible multiple layers. New memory technologies. That's very important. The fact is that now we have memory technology and memory architecture that emerge where we actually can start thinking about actually putting computation very close to the memory cells. Maybe even into the memory cell. And that's why 3D is very important. And again, our 3D devices are basically high. That's really what I want to do. So, what I'm not doing is artificial neural nets. Obviously, there's a lot of people thinking about that. It's called typically neuromorphic computing, the term that basically was invented, coined by Rabaey in 1989. And neuromorphic computing says I'm going to build a network of neurons. We figure out what a neuron does. We build the neuron is a new gate. We build a lot of gates, we connect them together, and we build big neural networks. And then you can find ways to program it to basically behave as and basically do certain algorithmic functions. So it's kind of reconstructing the brain bottom up. So I'm going to do the same thing that the brain does, but I'm moving to silicon or new other physical technologies, semiconductor technology. A lot of efforts going on this place. Europe is spending $1 billion in its brain initiative to basically build a giant brain simulator. They hope to simulate the complete brain from the neuron up with certain levels of accuracy. Now, if you want to do that, it's kind of power hungry. There's an effort, for instance, going on in Manchester. It's called Spinnaker. Spinnaker basically has they put about 1 million ARM9 processors together. Connect them together, basically it's 100 kilowatt, and can do about 1 billion neurons. Now, that's not bad, but basically it's a mouse. It's not a human. A human is about 100 billion neurons, with a factor 100 away from that. So take your 100 kilowatt by 100, and you just get 10 megawatt. Also, the human brain has about 1 quadrillion synapses, which is connections between neurons, wires basically. There's a bunch of other ones, Neurogrid, IBM, all of them, and Blue Brain, and so on and so forth. So that's all we're trying to do. This might be successful, but right now I think if you don't know the algorithms you're going to run, it's very hard to figure out what hardware you have to build. So it's lacking distance as well. There's progress. You might have heard about IBM's True Lordship. So I've been a lot of press about this recently. It's a neuromorphic processor, but it's a digital neuromorphic processor. It implements a bunch of digital processing elements, actually 64 by 64 cores on a single die. And each of them can basically simulate a number of neurons. Simplicity, they're not a complex neural model, but they're basically execute a neural model. They have local memory, there's some scheduler, there's some control, and there's a very nice asynchronous network between them. So you actually can have a random connection between. The beauty of it is can do about 1 million neurons, not a billion, not 100 billion, and 64 billion synapses at 70 milliwatt, which is an amazing number. That's actually a very good design. 70 milliwatt for this complexity, they really pushed hard on all the buttons they have from a design perspective. But again, that's not what I'm trying to envision what I'm going to talk about here today. I'm thinking about 1 layer higher. Okay, so how do we know how the brain works? Okay. There's very different ways. And again, if you look at neuroscientists around different corners. You have on one side the psychologist. The psychologist says the brain is a black box, and if I put inputs in it and I look at the outputs, I can predict ultimately what the outputs is, right? That's what psychologists do. And that's been used, that's where computational neuroscience went for a long period of time. So that's one way, it's not bad, but it gives you one perspective and you never understand the mechanism behind it. The other approach is the neuroanatomy of physiology. So I'm going to take a brain and slice it apart, and I'm going to build a netlist. Right? And again, people have done this. They're actually building a netlist of a mouse and a rat's brain. You take all the neurons and you look at all the connections, and you have a complete network of neurons. And you say, here's the network. But it's like I show you a joke. And it says, here's the netlist of all the gates. And then I ask you, what does it do? If I don't know what's in those gates, it's very hard to figure out what the functionality is. But at least it shows you what the networking and connectivity is, and that's useful information as well. And then the other one is what the computational neuroscience basically is all about, is they basically build models. They look at certain subparts. There's some experimental data, they look at some excitation, and they look at a measure, but they basically make a theory and they check it against real experiments. And then they basically say, here's an algorithm that might happen. This is something that may happen. And this is where I think a lot of the activity is going on today, because now we have the capability of doing the imaging, and we start basically to have the capability of checking the theories against reality. Okay. So that's the last one, is pretty much the corner I'm coming from. And I'm going to take one separate example. Obviously, the brain itself has so many different regions. There's motor functions, there's sensory functions, there's cognition area, there's reward systems, there's memory, there's all kinds of things in there. And some of them are better understood than other ones. The ones that are best understood are the sensory pathways. The 5 senses we have, how you basically take those senses and basically start going to multiple layers and basically make sense of what you basically observe. Okay. So let's have a look at one of them. Probably the most complex one. Of all the senses we have, vision is by far the most complex. So look at what's happening here. On one side we have the sensors. The sensors is the retina. Retina is an amazing imager. Has about 130 million photosensors, photoreceptors in there. So lots of data, very high resolution data. Now, if I would transmit all that data directly to the brain, you need a high bandwidth connection. Right? Now, the optical nerve that basically goes from the back of your eye to the cortical region, where basically the vision processing is done, is a bandwidth channel. It can do it's about 1 million fibers in a very narrow bundle, and total bandwidth or throughput is about 10 to 100 megabits per second. That's what it can send to the brain. So rather than what the eye basically does, what it does, rather than transmit all those sensory information in the raw format to the cortex, now basically the first thing you do is a visual layers of neurons sitting in the retina that do feature extraction. They extract some primary features. And the only thing you transmit to the brain is the features, not the image. So anything you see, or you think you see, is something you have reconstructed in your brain. It is not the actual image you see right away from the imager. It's a very interesting thing because that's why people sometimes see things differently. You learn how to basically interpret the information you get. So that's the first part, that's what I call the in-sensor processing. Come back to that. And then you go and you look at what's happening in the cortical region. Actually, vision is very complex. As I already said, it also takes a big part of the cortical region. Actually, the vision part is a big component. So we have multiple layers, V1, V2, up to V8. Each layer is higher levels of abstraction. You start with the primary features and then grow a little bit slowly, you work with objects and more complex scenes and so on and so forth. So you have layered hierarchical information. Now the interesting part is that you look at V1 and V2. Is the first region, that's where the optical nerve arrives. So you say, okay, now I have compressed the data. The natural thing to say is that I'm going to keep on processing this in this very sparse and efficient representation. And the answer is no. That's not what the brain does. The first thing it does when you basically arrive in V1 and V2, you see there's two big purple and red lesions. It does a massive expansion. It puts the data everywhere. It basically, suddenly it goes from a sparse representation to a giant overrepresented high-dimensional representation. So very interesting things happening here. They say, why do you do that? And I think, again, there's some good explanations for it. It's all about the fact that I want to do robust computation in the presence of very unreliable components. And be able to work with things that are approximate and not exact. So that's the picture here. So if I translate this, I'm an engineer, so I try to map this into architectures. And say, how is my vision on this? How would I basically put a block diagram of my sensory pathway together? And again, they're actually pretty similar for any sensory pathway. It's true for olfactory, vision, auditory system, senses, and smell. Taste, basically touch and smell. First thing is, you have a huge number of redundant sensors. They're not very accurate. They overlap. They don't do very precise. There's no sensor in there that can say, this is only reacting to yellow or that particular color or to this particular molecule for smell. No, every sensor basically senses a couple of them. And they overlap, and you have many of them. Then you have this first thing, which is basically called this feature extraction. You look at the sparsity of the information and say, okay, we're going to basically compress it, transmit it out, and then you have this projection into an overcomplete space. Massive, you get this, again, this is the first layers of the visual cortex. The red ones are the arrivals of where the optical fibers connect. and then you see this massive number of neurons where all this information goes. And again, pseudo-random. And then after that, basically, this is what's called this in-memory computation, associative memory type thing, classification, all this type of things that are happening afterwards. But again, 2 layers in sensor computation. The last one is primarily in-memory computation. And data is everywhere, and we're going to process the information based on its need. We're going to fire the computation when it's needed, when you basically need access to that data. Not opposite way, right? Like what we do today in computing. So the bottom line, what I might and realization of this is a lot of things has to do with how do we represent data. How do you basically think about data, how do you present it, how do we basically process it. And once you start understanding, then you can start saying, well, gee, maybe how would I build a neuro-inspired computing platform given the type of device I have? In sensor computing, in memory computing, I have new technologies arising. On both ends, we have a lot of really good sensory technologies arising. We can put some computation in there, we can do that. On the other side, we also can start thinking about how to do in-memory computation. So choosing the right information representation that makes computation easy, expensive, and robust, and matches the platform. Okay, so let's start with some examples. This is kind of the big picture. Let's go into some more type of real kind of implementation and so on and so forth. Again, various forms of data representation. Let's start with the front end. Low resolution and redundant. Why low resolution, by the way? And what type of processing will you do when you have low resolution? What's the advantage? Now, would you basically, the other question that you ask yourself is, why doesn't the brain do everything in digital? It basically doesn't use digital, does basically primarily an analog representation most of the time. Why does it do that? Well, there's some arguments about this. Again, this is something that is well known. People have studied this for quite a while. They say, okay, if I look at SNR, which is resolution, and the energy it takes to perform a certain computation at a given SNR. If I do a computation in analog, what you see is that actually if you don't want a lot of SNR, actually analog is darn good. I take a single transistor. It's actually an amazing device, right? It has a nonlinear function in it. You can do all kinds of multiplication with it. I can take 2 waveforms and multiply them. In a digital format, I need about 1,000 gates to do so. So analog in itself has a lot of computational efficiency, but basically getting high SNR is really hard. Because what you have to do is you basically have to deal with noise. Right? And the way you deal with noise, you have to make it bigger and larger and so on and so forth. So if you basically want to increase SNR, you can see that analog power goes up substantially. While in digital, the situation is just the opposite. Doing something at low SNR is hard, because any single gate takes about, 6 transistors to start with an AND gate, or 4 transistors, whatever it is. You take a number of transistors per NAND gate, and that's better. You can do only NAND. You want to do multiply, you have to put a bunch of those gates together, so you end up with a fairly large amount of complexity and energy for low SNR computation. But if you want to go to high SNR, the picture is different. Every time I add a bit in a digital representation, I have basically a factor 2 in basically, so just adding one bit is a factor 2 in SNR. That's just logarithmic. Every time I add a bit, I increase my resolution with a factor of 2. So it's an exponential factor. That's why you look at basically this particular plot that's shown right here. So digital, basically, if you go to higher SNR, it flattens out in terms of energy or power. So that's why you want to do high SNR. I go digital any day. It's much more efficient than doing analog. However, if I basically care about low resolution computation, just as the brain does, actually analog is very good. That's why most of the functions in the brain are done in the analog domain. Well, not why. This is why this is actually, they seem to be a good match. I cannot answer the why. Turns out this is true for communication, but it's for communication as well. You want to send a bit over a wire. Right? I want to send a certain, not a bit, but a certain amount of information over the wire. I can use a number of different representations. Or I can go digital, I can analog, and I can discrete time, all kinds of things I do. And again, you basically simulate it with all the noise issues involved and so on and so forth, data converters, all this kind of stuff. You still see that if you want to low SNR, do it analog. And analog or semi-discrete could be pulse-based is an analog representation as well as analog in time. So if digital is supreme and high resolution precision D, but analog is much more efficient at low SNR. This is why I think it makes sense if you start thinking about the very low, low resolution sensors that you deal with. You have lots of them. If I would think about what type of processing to do, I'm going to do low SNR analog. There's no reason to put A to D converters right there, right away, and just put it all in digital domain. Because it doesn't matter. It's basically the redundancy information of this device. And if you do so, you can do some interesting things. Here's, for instance, a circuit we built. It's one of my grad students. It's a front-end processor for a sensory processor, basically all artificial nodes, where you have a set of chemical sensors that basically look at various molecules, they're overlapping. And every sensor basically measures a resistance, actually the presence of a concentration of a certain molecules translates into a change of resistance of the sensor. Very simple concept. And you have a whole bunch of them in parallel. So in order to extract information, the first thing you would like to do is say, well, I'm looking, for instance, at a certain type of molecule or analyte. Concentration is another thing that modulates obviously the resistance. So there's the analyte, and this one information is what analyte I'm talking about, molecule I'm talking about, and then resolution. Turns out if I do right away transformation from the input to resistance domain into something which is spike-based. Basically, I'm going to feed that information. I'm going to go to some transformational logarithmic transform, feed it into a neural-like device, integrate a fire, and basically create a spike. Turns out that the information here, what analyte basically you're talking about, is determined by the pattern of those pulses. Not the size and the. Actually, if we change the concentration of the analyte, what it only does is get a phase shift of that pattern in time. That's the only thing it does. It delays it or it adds it earlier. At higher concentration, your neuron is going to fire earlier. So you create a pattern, and then the question of what analyte you're talking about is basically something which is just pattern recognition problem. That's a proxy. So I can move it on to the next thing. You have a set of spikes coming out of there, and then I basically can try to perform pattern matching on this. Now this analog processing, as said, this whole thing, this transformation, is very straightforward. It can be done with very simple transistors, analog devices. You can see right here. They can take about 15 nanowatt per channel, and they actually can run at fairly low voltages. And by the way, there's going to be variability, but it's no problem because the variability we learn. This is a learning system. We first calibrate it with a number of analytes. You learn it and you store the pattern. So that's an example of what you can do when you start going to this low signal. You really can start thinking about nanowatts of power for front-end processing. By the way, this graph on this right is probably hard to see, but you actually can start seeing the actual result of some of the spikes in various conditions from a simulation. Here's another example of doing processing. Very different way than we think about processing, but again, it's something that has been observed to be happening in the cortical region, in the retina as well. So you take an image, and one of the feature extraction you do is basically segmentations. You try to segment the image into different patterns. Right? You have an animal right there. What I would like to see is basically separation of the animal and the background information. Now, the way you can do that is you take a picture, you extract some features. That's the first thing you do, primitive features, which you then use as bait. And the next thing you're going to do is basically kind of solving a strongly connected component graph type problem, if you formulate it correctly. Now, the way I solve that particular problem is basically by having a bunch of oscillators, coupled oscillators. You have basically represent your data, and you feed the weights, the Ks, that basically go in the similarity graph, into a coupled oscillator, and you let it go. And as you know, coupled oscillators, when you basically feed them in some way, they're going to go to a certain pattern. And the pattern is going to be determined by the inputs you feed in there. So this is an example of a simulation of a large array of oscillators fed with information of an image, and you can see after a very short time, you see different regions form. These are the phases between the oscillators start shifting, and a number of oscillators go in phase. That's one region. The other ones go into another phase. That's another region. Again, interesting approach to solve a problem that we typically would solve using an algorithm, but can be done with very simple oscillators. Now, we know how to build oscillators very well. Most of the technologies that we have built are basically oscillatory type things. They know how to build oscillators very well. So, interesting approach to think about how to use some of the nano devices. Okay, so from that, let's move back a little bit from the sense of basically talk about sparsity. I said the first thing you do is extract sparse information. Sparsity is good because it means that you're going to have less components firing later on. Okay. Here's an example. Again, from image processing, video processing type of space. You take an image, xi, xy, and you want to compress it one way or another. Typical way you're going to do that is you have some waveform, wavelets, whatever it is, some transform, cosine, sine transform, whatever it is, and you're going to represent your image as a sum of those primitive waveforms, or patterns, or whatever it is. And typically you're going to try to minimize the number of primitive patterns that you're going to use to represent the image, and you basically get a set of weights. Now actually that's the wrong way. Or at least that's not the way the eye does. Actually what it does is something that's a lot more interesting. Basically it learns a set of patterns. A large number of basic patterns. And then when you basically compress the image, what you do is try to represent your image, it's here, as a sum of those primitive patterns. Phi is here, these are the coefficients, this is obviously a certain error factor. That's the error, you try to minimize the error, obviously. Okay. So typically you will have a small set of base functions and you get a large number of A's. In the sparse representation I would do the opposite. I take a large set of Phi's, huge representation like here, a lot of patterns, and you try to minimize the number of A's you're going to use. You try to force most of the coefficients to be equal to 0. Okay. And it works very effectively. You actually can solve this very nicely. So you can basically have a representation that preserves the information, the error gets minimal, the epsilon gets very small, and you minimize the number of A's, or you maximize the number of A elements that are going to be 0. So you represent an image with a minimal number of coefficients, if you have a large number of base sets. Again, that's a way of looking at sparse representations, which is different than what we have typically seen in the way we do image compression, where we try to minimize the number of base structures. And you can do this over and over again. As I said, the cortical region, they have this over and over again. Again, you see the same repetition pattern. This is from a paper by Bruno Alshausen in the late 1990s, basically showing this. And actually, it's quite a bit of inspiration of how we can do computation. Again, sparsity extraction is an important element. And it can be done, once again, sometimes quite nicely in the animal domain. Okay, now let's go to, I think, what is the most important part. Is this massively redundant, robust computation. Okay. How can I accomplish this? Right? That's a question that puzzles many. Both representation, can you do error correction? If I basically make my energy per operation too small, most of them will be wrong, then the error correction gets big and all this type of stuff. Right? You have a problem. So here's an alternative approach. It's called Hyperdimensional Computing. It's a theory that was developed by Ventika Nerva, this neuroscientist, again in the 1990s. That actually is a very good match to some of the things we're trying to do today. So here's the idea. Suppose I want to represent two things. Say I have one object, or two objects, and I want to recognize them, or I would encode them. So I say black and white. Two objects, one bit is sufficient, right? 0 is black, 1 is white, everything is happy. So 1 bit, 2 elements. Now the problem with that representation is if I make an error in that bit, the world flips around. Everything's wrong. Black becomes white and white becomes black. So very, very non-robust representation. Okay? And typically what we try to do in computation is say I have a number of objects and I'm going to minimize my state space. Right? Because that's the most efficient from a computational perspective. Now let's take the other way. Suppose I do something different. I said, I'm going to take, represent white with a huge random vector. Doesn't matter what vector it is, it's going to take a 10,000 bit vector. And I pick it randomly and say that's black. From now on, this is black. And I take another one, randomly generated, 10,000 bits, and I say that's white. Now, if you think about it, if you look at the distance between those vectors, the Hamming distance, by XORing the two, you will see most of the time, if you take a purely white noise random distribution, you will see that 50% of the bits are going to be at least different. The chances basically are, the probability they're going to be equal is about 50%, right? So every one of those vectors is going to be 5,000 bits apart, on average. But actually, as I'll show you in a second, actually that distribution gets actually smaller. The distribution, the variance on that distribution is smaller with larger vectors. So it means that I have a vector of 10,000 bits, and I flip 4,000 bits. I still know for sure that black is black and white is white. You can have huge amounts of errors, it doesn't matter. And it actually still is a robust computational representation. And again, this is a pure binomial distribution. If you just go do the standard statistical package and look at basically the histogram of the distance between vector and n-dimensional space, you have a very small dimensional space, distribution is quite low. You know, vectors, random vectors can be very close to each other, can be very far. If, however, the number of vectors gets larger and larger, you go to 10,000, you see that almost all the vectors that I can create are going to be 5,000 bits away from me. Yeah, I take any random vector, it's always going to be 5,000 bits away. It is pseudo-orthogonal. You cannot say it's orthogonal for sure because it's a statistical process, but it's going to be pseudo-orthogonal. So I create random orthogonal vectors. Now the beauty of this is that it's very robust against failure mechanism and noise. I can run at very low SNR and still get robust results. It thrives on randomness. The better I can generate random vectors, the better I am off. So this is something which is kind of different, right? And the last one, which is very important, is a complete algebra. They say if I want to do computation, I want to have a number representation, I want to have an algebra. You can compute with those things. You can do all kinds of fun things. It is, however, if you start thinking about 10,000 bit vectors, and you try to do that in traditional memory architecture, that's a disaster. I have to get those vectors in and out of memory is really painful. But if I start thinking about this 3D integrated memory structures, actually becomes a lot more efficient. And actually can start putting those computations on those vectors inside the memory. You have a different game. So, interesting perspective. So, think about this. Here's how you can do some computation here. If you do, let's say, again, you take a standard computing language and you say, I want to have a data field. Like I have a person, and I have some information about the age of that person, the gender of that person, and the ethnicity of that person. What I do is I create a data record. A data record with fields, and that field is going to be age, and that field is going to be the name of the person, the gender of the person, and so on and so forth. So you have a number of bits, and you represent it as fields. Now, if you go to a hyperdimensional representation, you don't do that. Your data actually is kind of a pattern in this hyperdimensional space. It's 10,000 dimension space. And I overlay the information. Basically, I say, well, I'm going to take x is equal to a. That's going to, let's say the person has an age a. X is age. A is a number. Y and B is the same thing. And you basically keep on ending XORing with each other. And you overlay the information on top of each other. You create a new vector of 10,000 bits, which is the combined information. And if I basically want to enroll this, I can basically do the inverse operations on it. But the data is not in a single place, it's everywhere. And I take some part away, it doesn't matter, I still can get it out there. Because it's so redundant. And that's the way a brain works as well to a certain extent, right? I basically, as you think, they might have heard about this thing which is called the Mona Lisa neuron. And if you go and see the Mona Lisa, how do you know it's the Mona Lisa? Okay. Well, it turns out there's actually, for pictures that are very common to you, that you basically recognize very well, there's actually a single neuron that's going to fire very extensively. It's very much trained to it. Now, if I now zap away that Mona Lisa neuron, will you not recognize the Mona Lisa anymore? And the answer is no. You still will recognize it. You still do a good job at it. It might not be so fast anymore, but there are more elements. But basically, it's the fact that the information is not in one space, but distributed basically makes this thing very robust. Same idea. And so you can do multiplication is binding, and bundle is basically combining fields together. And you can basically put information together, you add them up, and so on and so forth. A bunch of this that basically happen. And occasionally you want to clean it out, because every time I do an approximate computation, you go somewhere in distribution, occasionally I can map it back into the real value. So let me show you an example here. using random indexing and associative memory based on hyperdimension. Very simple example, identifying languages. You see, I give you a sentence and I say, what language is it? Right? So here's how this works in a hyperdimensional space. This is, again, work of Nerva. He took 21 languages and took from every language 1,000 sentences. Okay? Now, letters only. There's no semantics, there's no nothing, it only knows sequences of letters. It's the only thing he's basically looking at. He extracts some features, so you get that text, and the first thing he does, he takes a sentence, and the first thing he does with that sentence is turns it into a single 10,000 bit random vector. Okay? And stores it in the memory. And he keeps on doing this with more vectors, he combines it, and in the end, the whole language is represented as one vector of 10,000 bits. And then he says, well, that vector is now Dutch. So in the end, you have 21 languages, so you have 21,000 vectors, but ultimately you have 21 vectors totally of 10,000 bits. Stored in memory. And now, if you want to retrieve a sentence, you just put in a sentence in there, you do the same random indexing, you map it in this large 10,000 bit space, you feed it in there, source the memory tries to find the best vector that matches the input vector you have, the closest one, and out of this comes your language. And this works with about 98% accuracy on the language we talk about, which is pretty good. Now, you may say Google can do this same thing. Now, Google basically does this with a lot more complex in terms of algorithms, that's one thing. And the second thing, you use a lot more data. This is done on a very small data set. So this can be done, now, obviously right now, if you implement these things on a statistical computer, it's going to be darn slow and very power hungry. Again, think about the opportunities of the architecture that we're talking about. And you can apply this to speech to music, is actually a general concept. It is not basically limited to anything. So the key element you have to build to do this is something like that looks very similar from literature to use. It looks like a memory, doesn't it? So somewhere you have a decoder and you have a memory array, but that's where the similarities end. Because first of all, I have here this associative memory address matrix. That's a random mapping. Basically, any time you feel a vector in there, it's going to map it in a random space, and it's not going to give you a single address that's the correct one. It's actually going to basically pick a number of them. And then the second thing what you do is that memory unit, context memory, that's basically a matching matrix. Basically, going to try to find the vector that's the closest. It's not like a typical associative memory. You put an input and it gives you one flow. It actually will give you the closest one. So it does distance computation included into it. Now, by the way, this is the structure that also appears in the basic cerebellum. If you look at cerebellum in the brain, very much the same structure. You have a decoder thing right here. You have your memory rate. You have your output. And the larger the array, the better it gets. Now, what's cool about this? The interesting part is that that's another computational paradigm that can be executed in a computer. It really matches very nicely with some of the devices I've just been talking about. If you talk about a random number generator, I know how to do that. I have really lousy components. I have basically memory cells that things like that are all over the map. If I combine them in a cluster and I basically combine them together, I basically can create wide vectors. This is something, a project we're doing together with Stanford, Philip Wong, and Subhashis Mitra, where we stack like the RN cells on top of carbon nanotubes as basically variable delay elements. And we use the variable delay elements to create very random vectors. That's basically my decoder right there. Basically implemented using the 3D technology. And it doesn't matter if not all the corrections of the connections are correct. Randomness is something we give. As long as it stays the same over time. Same thing with the other part, in memory computing. We can start thinking about building these associative memories in your traditional memory, but that's not easy because I have to have a structure like this. But at least I can show you why it's good. It turns out that if I implement these associative distance vector computations and I have random variations in my process, I push down the supply voltage, that varies basically gets really large, it turns out it gets better. Right? So it's a good feature to have. And by the way, since it's all basically sparse, spike-based, we only turn on the part of the memory that's needed. Most of the memory is quiet. Most of the time we just turn on a small fraction of the memory point in time. So from a leakage perspective, it doesn't matter either. Leakage is actually very small, doesn't matter. So variability and leakage are overcome by this particular strategy. Which is coming back to the beginning of my talk, So this is what we try to do, overcome leakage and variability. So these are a bunch of components. This is what we're trying to build as we speak, analog prominence sensors. So this is actually building olfactory artificial nose with sensory inputs first, basically random mapping, and then following in-memory computation. And our goal is really to put it all together into one single system. All right. So basically, to summarize, I think this is exciting. I think it is true that we learn a lot about computation. I think this work that Pentti has been doing about the fact that patterns of neural activity are not really associated with numbers. That's an important thing. The data is not represented as a number, but basically as a pattern that's stored through your interconnect and the weight factors on your neurons in your brain. That's an interesting thing. Now we have the technology, so we have the computation. Now we can bring the two together. Is this the end? By no means, right? Again, this is just top of the iceberg. Nature or biology is hiding the secret well, and basically getting them out of there is something that's taking time. Now, again, as I said before, this is not something that only us are observing. Actually, if you think about it, Neuro-Inspired Neuromorphic Computing is quite common. I showed you the neuromorphic chip from IBM. Qualcomm has, a year ago, 2 years ago, announced their zero law processor, again, a neuromorphic processor. Deep learning is amazing. It's really making things change fundamentally, and things like robotics. You might have seen this recently. This robot that basically learns how to take up a bottle and learns on itself without any inputs how to basically unscrew the cup. No learning basically figures it out, it tries, and after a while it is better and better and better, and does the thing. There's no algorithm behind it at all. It's all based on deep learning. People have shown that actually computers can learn how to play a game without ever knowing the rules. They just watch what's happening with the game, they look at the output, they see the score, and they basically try to figure out it. So deep learning is another example of other things. And there's some serious startup activity going on as well. So there's a lot of things happening in this space. So final reflections. So Neuro-Inspired inference computing, I think might be a good match to the next generation of devices. And maybe help us to basically extend Moore's law, or whatever law you want to name it, into the future. Prime target is not your traditional computing. It's really the fact that we're going to deal with lots of data, and we're trying to make sense of data. So the things that are happening in the cloud, as well as the swarm, the IoT devices are playing. Obviously, it's always nice to have generalizable solutions. You don't want to make a new solution for everything. General concepts are really crucial, and that's really important for the academic world to think about this. And obviously, this is not something that you do on your own. It really requires understanding of devices, architecture circuits, as well as algorithms, neuroscience, and so on and so forth. So it basically requires collaboration. Now, all this work is done with a number of people, and primarily funded by the Sonic Center. Sonic is a center which is funded, multi-university center, funded by the semiconductor industry as well as DARPA. It's a 5-year center, and this is one of the big factors that basically we're trying to do in this center. Thank you for your attention.
So we'll take a moment to have some questions. Does anybody have a question?
Yeah, I have.
Sure.
Moore's law is almost ending at 10 nanometer or lower.
Mm-hmm.
Where these devices will come from, silicon or some other chemical?
A good question. I'm not going to make, silicon obviously has its role, but it's also clear that silicon has its limitations. So a lot of the devices that I see that go beyond are non-silicon. And again, it could be carbon, could be other type of structures out there. But don't count silicon out. Actually, a lot of the solutions we're looking at are basically hybrid, where you have a silicon substrate and you build layers of device on top of it. But again, that's crystal ball gazing. There's a bunch of devices out there. Which one is going to gain and which is going to play this? We don't know. Yes.
Wouldn't spread spectrum communications be an example of hyperdimensional already?
Mm-hmm. Yeah, it's one way of looking at it. Indeed, you basically randomize the data over a certain base. No, absolutely. So we have a big discussion going on right now about this hyperdimensional computing and how this fits with Shannon. Everything always goes back to Shannon. And Shannon already had this idea of random codes way back as a way of representing data. And he had some theories about this as well. So we're actually trying to figure out theoretically where all those things fit together. But if you did can mash this all into one theoretical framework, that's quite nice, and we can start thinking about capacity and things like that, capacity versus energy. These are all interesting numbers, interesting things to think about. But yeah, people have been thinking about randomization as a means of basically creating orthogonality. Thank you.
What happened with entropy and information? Let's say I have a number of states, initial conditions, I have a computing device, and I have a power supply. And then I came to the answer. What happened with information and entropy?
So ultimately, the key thing you're trying to do, if you look at computation, right, it's a question of are you reducing entropy or what are you doing when you go through multiple steps? Right? Entropy is not the same thing of a single device or anything like that. The entropy is of the whole system at large, right? So I think from an entropic perspective, what you're trying to do with this type of representation is spread it around over a much larger space. I don't think you basically change fundamentally. Well, you might actually increase the entropy to a certain extent. But the fact is that in terms of what I'm going to basically going to need from an energetic perspective to basically compute on stuff of things, is going to be the steps to do transformations or reducing entropy are going to cost me less. That's kind of one of the possible implementations you can talk about. But again, these are good questions. Again, there's a lot of interesting things you can do on a theoretical level. This has basically been around, the hyperdimensional stuff has been around for a number of years, but it has been, I think it's nice if you start suddenly say, hey, let's have some information theorists kind of take a tack at it and see how they interpret the information about basically the model. And where, if it changes any bounds, and probably will not, but if it allows us to get a lot closer to those bounds, right? Again, if you think about limitation on computation, we have on the other side, we have the uncertainty principle, which is also a result of Shannon in some way. The uncertainty principle basically says the minimum energy for a digital computation is about KTLM2. We're about 5 orders of magnitude away from that because of a set of implementation reasons. It doesn't change anything about the representation, it's just that the implementations are inefficient. So if you can get close to those numbers by making our computation more efficient, we basically are making a big gain. We don't change fundamentally the entropy of the system itself or the information itself. We just make the transformations more efficient.